Hello, this video is meant to help you walk through the procedure for collecting your velocity data. So we are in Ball Lab Part 1, and I want you to scroll down. You should already have completed your quadratic best fit. You already completed your general mathematical pattern for displacement time, your leading coefficient, your y-intercept, and your best quadratic fit for displacement time, as well as your processing questions for displacement time. We're moving into kind of the second half of this lab, which is another experimental setup, this time looking at how the time affects the velocity of the falling ball. And you'll see down here for our dependent variable, we are going to be measuring that velocity by looking at the slope of a tangent line. That's strange. Let's scroll down, and here's where we're going to pick up together. You should meet me at the Finding Velocity title. So you should remember back from last unit when we looked at the car lab that the slope on the displacement time graph represents, that's right, that represents the velocity. That's how we found the velocity of our car. We collected time and displacement data, we graphed it, and we looked at the slope. Now, last unit in our car lab, we had a linear best fit on our displacement time graph. But now we are not seeing a linear fit on our displacement time graph. So last unit with the linear fit, we had just one slope. But now with this curve, this quadratic, this parabola fit, we have more than one slope. You can kind of think of this as like the slope down here is really shallow, and then it gets steeper, and it gets steeper, and at the very end our slope is pretty steep, it's very big. So our slope like almost keeps changing. So how are we going to figure out the velocity from the slope of this displacement time graph, knowing that the slope is always changing? Well, we're going to use something called the tangent line. And we are going to find the slope of that tangent line to help us out. So what is a tangent line? A tangent line is simply a line that is going to touch the curve at just one point. So you can see in this picture that the green line is our tangent line, and it's touching our curve, maybe this is our best fit parabola in red, at just one point. So if we could find the slope of the tangent line, and then find the slope of the next tangent line and the next tangent, and we can kind of step through the different slopes of the different tangent lines in order to find our velocity at each of those moments. So that's kind of our game plan. But I'd like you to pause the video right now and give your brain some time to process this. I want you to summarize how are we going to find the slope and therefore the velocity at each moment on our displacement time graph. Pause now and answer in your own words. Okay, now that we have our game plan in order, we're going to carry this out to the best of our abilities using Pivot Interactives. So you'll notice I have my Pivot Interactives graph. That's what I was working with before. So you want to make sure that you have Pivot Interactives open and you're signed in. You should have your displacement and time data already entered from Ball Lab Part 1. You should have your displacement time graph, and that quadratic should be showing, that quadratic best fit should be showing on your graph. And under your graph where you should have that quadratic best fit equation. So make sure you're at the same point that I am. If you need to go back, how I got to this point was following the instructions for number 1 through number 12 on pages 1 and 2 of this document. Okay. So our goal right now is to collect velocity data. If you take a look at the graph or at the data table coming below, we have lots of velocity blanks to fill in. And remember, we're going to be looking at the slope of those tangent lines in order to collect that velocity data. So I want you to come over in Pivot Interactives. This is number 13 in the procedure. we're going to click on that little gear in the upper right corner of your graph and hit Curve Fits to pull up our menu. And let's go ahead and get rid of that quadratic fit. We're going to go to a no curve fit. So we're going to just reset ourselves. You should see no best fit on your graph anymore. So since we want the tangent lines, we're going to need to start to add a linear fit. So I'm going back right into that gear again and curve fits again, but this time I'm going to select linear. And you'll notice when you click done, this line shows up on your graph, and it's a pretty bad fit for our data because after all, our data is not linear. What we do want to do with this line is try to set it up so the best that we can get the slope of small little tangent lines so that we can learn about the velocity at those moments in time. So I'm going to come to my farthest right data point and I'm going to click right on the data point itself. Take a look what happens when I clicked on that data point. You can see that this little X shows up next to my displacement. And if I move my cursor, my data point is now a big X. What that X means is that Pivot Interactives is no longer using that data point, the X data point, included into the linear best fit. This is really good news for us because that means that we can start to make our line, applicable to only parts of our graph. So I'm going to go through and I'm actually going to X out all of these data points. It can be a little finicky at times to make sure you actually get the X. And I'm going to leave just the first 3 data points. Okay, so you should have your time of 0.0500 seconds, 0.1000 seconds, and 0.15000 seconds. So our first 3 data points are selected. Now you might be thinking to yourself, isn't a tangent line going to touch at just one point? Well, you're right. Ideally, a tangent line is just going to touch at one point. Unfortunately, if you try just one point in Pivot Interactives, well, it doesn't really help us too much. It just shows a flat line, and I don't think that that's right. So instead, we're going to do the next best thing. We're going to highlight 3 points. So our first data collection is going to be with those first 3 points highlighted. And if you scroll down, I'm on step number 22 and 23 here. If you scroll down, you're going to see that linear equation best fit of the form y equals ax plus b. It's very similar to what we usually say, which is y equals mx plus b. And I can see the slope of that line. That slope of that line for me is 1.40 meters per second. This is excellent because that slope, take a look at the units meters per second, that slope is our velocity somewhere around these beginning times. I'm going to scroll down to my data table. Of course, you would have already filled in your control variables, copied them from Ball Lab Part 2, all that good stuff. But I'm looking at the first 3 points highlighted. And I'm going to record my velocity, my slope, 1.40 meters per second. Remember, you don't have to write the units in the data table itself because they're already in the column header. I'm going to repeat the same step, but I'm now going to highlight points 2, 3, and 4. So I'm going to unhighlight my bottom one, and I'm going to highlight my next one. And you'll notice my linear fit got slightly steeper. My slope has increased, my velocity has increased. And here is my slope of my new linear fit, my velocity. I'm going to record 1.70. I'll move on to the next part of my data table, highlighting points 3, 4, and 5. I'll uncheck that and include that. And again, it got steeper. This makes sense with what I would expect for a parabola. Looking at my slope, 2.5 meters per second, recording that as my velocity. You're going to keep repeating this, highlighting different points at each different level. And each time you're going to be recording that slope of the closest to a tangent line as we can get, recognizing that that slope is your velocity. Okay, so I've finished collecting all of my velocities. I just want to do a quick sanity check here. It looks like my velocity is increasing as time is increasing. Does this make sense with what we were seeing on our graph and the slope? Does this make sense with your qualitative observations of what it looked like when a ball was falling? Okay, next up, you're going to go into graphing this velocity time data. You're going to look at a second graph in this lab. Happy graphing!